In this video, we are going to be learning about frames and simple machines. We're going to learn how to evaluate these systems and learn their different quirks and nuances. So, let's start out by talking about what is a frame. A frame is a rigid body that is made up of different components that have fixed pieces. So these corners right here where the different components connect to each other are completely fixed. This 90-degree angle here and here will stay 90 degrees at all times. It cannot change from being 90 degrees. That's what is meant by a frame. So, moving on to simple machines. There are lots of different examples of simple machines that you might see. Some of the popular ones include pulley systems, or things like wrenches, pliers, fingernail clippers, etc. So, what are the biggest tips for solving these problems? The first thing is to always start by drawing a Freebody diagram. Always draw a Freebody diagram. If you can draw a Freebody diagram, we can use the skills that we've learned previously to solve these problems. The next thing you want to remember is to break down the system into individual components. This will allow you to evaluate smaller pieces of the system that are related to the other systems and solve for your unknowns quicker and easier. Another thing to remember is that choosing which piece to start with is arbitrary. Now, there is different ways you can recognize which starting point is going to be easier for you. However, if you can't recognize that at first when you start learning these, then just pick a piece and start moving forward, and over time you'll be able to develop that sense of which piece is going to be easier to start with. All right, so those are just some quick tips to remember when solving these. So let's run through some examples of frames and simple machines. Let's go ahead and start with a frame example. So let's just say we've got that funny looking frame right here. It's going to be fixed into the ground. moment connections at each of these 90-degree angles. And let's stick a point load here of 10 pounds. And let's stick a rectangular distributed load up on the top here. And let's stick a uniform distributed load on this bottom section. We're just going to keep this as 2 PLF, and up here we'll have 10 PLF. And to add dimensions, I'm going to say this is 10 feet. We'll say this is 10 feet. And then we'll say this top section here is 2 feet. All right, and let's label this point down here A, and let's find reactions at point A. Now, this example is more like evaluating for equilibrium of a rigid body, because we don't have any individual parts that can be broken off in this case. So we're of course going to start with our free body diagram. And in drawing a free body diagram, you always start with your system or your component that you're looking at. And then you can apply the forces. All right, that's 2 PLF. And then apply your reaction forces. So we're gonna have a reaction in the Y, a reaction in the X, and a moment reaction A. Okay, so now that we've got that, we can use our equations of equilibrium to solve for unknowns. So again, I always like to start with sum of moments about a point. So let's do our sum of moments about A equals 0. Choose a direction. I like to choose clockwise. And I always like to pick one end of your system and move to the other so you don't miss anything. So in this case, I'm going to start at the bottom and work my way up and then to the right. So AY and AX won't cause a moment because they go directly through point A, so they're just going to cause translation rather than rotation. So those don't cause any moments, so we can go ahead and move on. So we've got a negative MA, and then we've got our uniform distributed load, which is going to cause a positive moment. So 2 PLF. times the length of the distributed load, which is 10 feet. Again, this is just the area of a rectangle, and then times its moment arm, which is going to be the length of 10 feet divided by 2. Because the centroid of a rectangle is half its length. Okay, now we can look at the triangular distributed load, and that is also going to cause a positive moment. So we're going to do 1/2 times the base, which is 10 feet, times height, which is 10 PLF. Again, this is just the area of that triangle to get you a force. And then we need to multiply it by its moment arm, which is going to be the perpendicular distance from the point we're taking our moment about over to the centroid of that triangle. So that distance there is going to be 2/3 of 10 feet. Again, that's just the distance from point A over to the centroid of that triangle. And then we've got this 10-pound point load over here at the other end, which is also going to cause a positive moment. And its moment arm is going to be 12 feet. Because again, that's going to be the distance from the point we're looking at, which is here at point A, up to that force. So that's going to be 12 feet. All right, and that's equal to 0. So we can now solve for our unknown. You just plug all of that into your calculator. Double check that I plugged that into my calculator correctly. 2 times 10 times 5 plus 5 times 10 times 2 times 10 divided by 3 plus 10 times 12. Okay, so I get 553.33 pound-feet, and that's positive, so we assumed our direction correctly, so this moment is going counterclockwise. Great. Now we can move on to our sum of forces. So I'll start with sum of forces. X equals 0. I'm going to choose to the right being positive. We can go ahead and start that equation. Again, I'm going to start at the bottom, move up, and then to the right. So we've got a negative AX plus our uniform distributed load, 2 PLF times 10 feet. And then for our, again, this is just the area of that rectangle. And then we're going to have our point load, which is going to be a plus 10 pounds equals 0. You can solve for AX, which is going to equal 30 pounds. And that's positive, so we know we assumed the correct direction over here in our free body diagram. So we know that it goes that way. Now we can do our sum of forces Y. Again, I'm going to start at the bottom, move my way up, and then to the right. So we've got AY, and then we're going to have our triangular distributed load, which is going to be a negative 1/2 base, which is 10 feet, times height, which is 10 PLF. And that's the only force acting in the Y direction. So that's the rest of our equation. That equals 0. So we know that AY equals 50 pounds. And that's positive, so we assumed our direction correct in our free body diagram. So that's going to go up. And that's how you solve that frame. So again, not very different from what we did in equilibrium of a rigid body. So now, moving on to simple frames. Let's go ahead and look at a pulley system. So let's just say there's this box or crate of some sort, and it's being held up by some rope that is attached to a pulley. And one side of this pulley system is attached to the ceiling, and the other is attached to a different pulley. Again, that side being attached to some ceiling component. And then this one will wrap around this pulley. And that pulley, which is attached to that pulley. That's being attached to the ceiling. And we'll do one more for good measure. And you're pulling down with some force. Now, let's say this crate weighs 500 pounds. And we want to find the force F that will hold this system in equilibrium. All right, so remembering our tips from above, always start by drawing a free body diagram, break down the system into individual components, and then your starting point is arbitrary. So for me, I always like to start at the side with the box because we have a known weight, whereas if we start on this side, we have an unknown force and you have to carry that unknown all the way through. I just like to have knowns, so I like to start with the crate because we know what its weight is. So let's start by drawing a free body diagram of the crate. So you start by drawing the component itself, which is our box, and then you apply forces, which in this case is going to be its own self weight, which is 500 pounds. And there's a string attached to this box that's attached to a pulley, which is pulling up on that box. And we'll call that tension 1. So now that we have that, we can do our sum of forces Y, which we have a negative 500 pounds plus T1 equals 0. You can solve for T1 and know that it equals 500 pounds. And now you just work yourself through the system. So we're just going to do that pulley right above, which I can label these pulleys as A, B, C, D, E, F. So now we're going to do pulley A. So again, you draw that pulley. We know that the rope attached to the center of that pulley that's attached to the box is pulling down on that pulley. And if you can't visualize that, when you go from component to component, these forces are going to be equal in magnitude but opposite in direction. So we found that this one up here is going up, so this one needs to be going down on this component. So we know that this is T1. And then we have other pulley ropes pulling up on this pulley. Now, one thing to remember about pulleys is that the tension force on one side of the pulley is going to be equal on the other side of the pulley. So we know that this force is going to equal this force. So we can just label these both T2 because they're going to be the same. Again, you do a sum of forces Y, and you get negative T1 plus 2T2 equals 0. We solved for T1 already, so we can do negative 500 pounds plus 2T2 equals 0. And we can solve for T2, and it's going to equal 250 pounds. Now, again, we just keep moving through the system, so we can now free body diagram pulley B, which is going to be extremely similar to pulley A, except now we have T2 pulling down on it, and we're going to have T3 pulling up and T3 pulling up. Again, sum of forces Y. And we're going to get negative T2 plus 2T3 equals 0. But we know T2, so we can go ahead and plug that in. So we can solve for T3, and that's going to equal 125 pounds. All right, and we'll just keep moving through this system so we can do C now. And for C, we've got some force pulling up, and we have T3 pulling down on it. And because our question is just asking for the force F, we don't need to find this reaction force here, so we can go ahead and just move on to the next pulley, pulley D, because we already know what T3 is. So again, we're gonna have T3 holding that up, and that's already known. So we can go ahead and move on to pulley E. Which has T3 pulling down on it. And what we'll call T5 pulling it back up. So again, we can do our sum of forces Y. Negative T3 plus 2T5 equals 0. We know what T3 is. So we can solve for T5, which is going to be 62.5 pounds. Now we can keep moving through to our final pulley, which is F. And we've got some force holding that up to the ceiling. Our force F, which we're pulling down on it. And then over here, we've got our T5 force. Again, we're just being asked to find T5. So this force doesn't matter to us, but we know that the forces on either side of the pulley are going to be the same. So we know that F is going to equal T5. So therefore, F equals 62.5 pounds. So how awesome is that? We have a 500-pound crate that we're trying to lift, and we only have to pull with a force of 62.5 pounds to get that crate to move. That's why pulley machines are so beneficial. So there are many other examples that we could go through, but I think that gives you a good enough start for now. If you have any specific questions about homework problems that you're working on as far as simple machines or frames goes, feel free to reach out to us. Head over to our homework help page, and we'll be able to answer specific questions about your homework problems there. If you're just having struggle completely with one of these problems, go ahead and head over to our tutoring page, and we'll be able to get you more comprehensive help there with a tutoring session. If you have any questions in general, feel free to send us an email. Taylor's Tutoring, etc. at gmail.com, or you can go ahead and use the chat function at the bottom of this page.